learners, this is Education Online program. Our subject is chemistry and the topic is Graham's law of diffusion, and it is for senior 3 and 4. So I'm teacher Lily going to take you through this topic. So learners, what is this Graham law of diffusion? So this law here is explaining diffusion where in gases. So here this scientist called Graham, which we name this topic as this law as Graham's, because he's the one who discovered that gases, he studied how fast gases travels through the air. So particles of gases and liquids move from area of higher concentration to an area of low concentrations. So this area of low concentration until they unified is spread out through the environment of low concentration. It means until they reach equilibrium. So there are gases or gaseous molecules that move through a concentration of higher concentration to an area of low concentrations. So what is this diffusion? So diffusion here is a movement of molecules from region of higher concentration to a region of low concentration. So until it reaches equilibrium. It means when they are now balanced, then it will stop diffusing from higher concentration to a lower concentration. It means they are now having equal concentrations. So diffusion is a daily phenomenon in our daily life. So we should put this one down and then we continue knowing what is this Graham's law of diffusion come about. So we can say Graham or Thomas Graham studied how fast gases travels through the air. Thomas Graham studied how fast gases travel through the air. So here we can say that not only particles of gases that can travel from through the air, but you can have also liquids that can travel through the air, or moisture that can travel through the air. So we call this process as diffusion. So we say diffusion is the movement diffusion of gases is the movement of gaseous molecules from a region of higher concentration to the one of low concentrations. From a region of higher concentration to the one of low concentration until it reaches equilibrium until it reaches equilibrium. So we shall have to know that this diffusion law, and we know that diffusion is a movement of gaseous molecule or any other molecule from a region of higher concentration to a region of low concentrations. So diffusion is our daily phenomenon, and it is there in our daily life. So diffusion is important in a number of real life situations. You can have diffusion diffusion is our daily life diffusion is our daily life experience. It's our daily life experience. For example, you can have the diffusion of perfume. You can find people use of perfume by people to avoid the bad smell of sweating. So you can have the perfume diffusing, or the gas of the perfume. Of course, perfume is made from gases, and it diffuses into a human body, and it takes a bad smell, and this is done through diffusion. So use of perfume by people. So when you spread perfume over your body, then it will take bad smell out. It will have a very good smell, and this is actually done through diffusion. It diffuses into your body. So also you can have the diffusion of tea bags. There are tea bags, and you want to make tea. It means when you put it inside water, then there is diffusion from the tea bags into the tea. So at least you can have the tea you wanted, for example, in black tea or red tea. So you can have this as an example also. Diffusion of tea bags. Diffusion of tea bags to make tea. So these are some of the few examples, but there are many that we can encounter in our daily life. So we can say that there is rate of diffusion of the gases. So this have been established that different gases diffuse at different rates. So different gases diffuses at different rate. So chemists refer to a gas traveling through air as diffusion in air. So chemists define this as diffusion in air. Before air moving through for this gas moving through the air, we call it diffusion of in air. And the speed with which this happens is referred to as its rate. So the speed of this gas is moving through the air, we call it its rate. So we can say that the rate of diffusion of gases, we can say that the rate of diffusion of gases is equals to the distance covered divided by the time spent. So this is actually explained through an experiment whereby a chemist try to see that a gas traveling through an air is gas traveling through air gas traveling through air, and this we refer to as diffusion. Diffusion in air. Diffusion in air. So we call this as diffusion in air. And the speed with which the speed with which it travels, the speed with which it travels, it is called the rate, or we call it as its rate. Its rate. So this is known as the rate of diffusion. Now this rate of diffusion, we can calculate it from the distance over the time. This is the first experiment that the scientists did in order to get the rate of the diffusion. For example, you can have the rate of diffusion of ammonia, rate of diffusion of ammonia gas. Of course, it is a gas of ammonia is equals will be the distance over the time it takes. So the distance for ammonia gas to travel through the air, whereby we consider it as diffusion in air, the distance is 12 centimeter cube. So we divide this by the time it is spent to diffuse. So the time it is spent to diffuse is 5 seconds. So at first, the scientists discovered that you have to get the rate of diffusion of any gas by knowing its distance that it covers and the time it takes. So with this, by dividing 12 over 5 seconds, we can have this is as 2.4 centimeter per second. So this will be the rate of diffusion of ammonia. So the rate of diffusion of ammonia will be 2.4 centimeter per second. You can also have hydrogen gas or hydrogen chloride gas as the rate of diffusion of hydrogen will be equals to 8 over 5 seconds. So when you divide this, and we can have the rate at which a hydrogen chloride gas travels through the air. So this will be 1.6 centimeter per second. So this is at first how the scientists are getting the rate of diffusion of gases. So here we can say that the rates of diffusion of gases depends on the molecular mass. So here this is another way of knowing how do we get the rate of diffusion. So the rate of diffusion of gases depends on the molecular mass and the density of a gas. So actually this rate of diffusion depends on the molecular mass and the density of a gas. So we can come out and we see how we get the formula for getting the rate of diffusion, or we can say diffusion at large. So we can have that the rate of diffusion of gases depends on the molecular mass and the density of a gas. So rate of diffusion rate of diffusion depends rate of diffusion of gases depends on the rate of diffusion of gases depends on the molecular mass of the molecules of gas that travels and its density and the density of a gas. So we can have these two items. They are very important also when we are getting the rate of diffusion, which is the molecular mass and the density of a gas. So we shall have this as this was discovered by Graham. This is whereby Graham's enter in, and he also said that the rate of diffusion cannot depend only on the distance and the time it covers, but it also depends on the molecular mass and the density of the gas. So we shall say that here Graham's go ahead and compare the density of the gases, of the different gases, and their rates of diffusion. He went ahead and compared the density of different gases and their rates of diffusions. So he found out that a less dense, so Graham's found out that the less dense gas diffuse through a medium faster through a medium or through any medium faster than through a medium faster than the high dense gaseous molecules. So we shall have to say that those with the less dense travels faster than those with the higher dense. So in this case we shall say that here, based on this observation, he formulated a law which says that Graham's law states that the rate of diffusion of gas, which states that the rate of diffusion of gas is inversely proportional to the square root of the rate. So Graham's law states that the rate of diffusion of gas is inversely proportional to the square root of its density. And provided the temperature and the pressure are kept constant. Provided the temperature and the pressure remains constant. So we can have to say that this law of the Graham's law of diffusion, we say that the rate of diffusion of gas is inversely proportional to the square root of its density. So here the rate of diffusion, it means it goes together with the rate of diffusion, it goes together with the square root of the density of the gas that travels through the air. So this, as you kept the temperature and the pressure, the temperature and the pressure remains constant. So this is how Thomas Graham came out with this law, and this is the law of the diffusion of the gases, and this is expressed mathematically as rate of diffusion will be equals to the rate of diffusion will be, which is represented by R, will be inversely proportional to the square root of density. So this is how it is mathematically expressed. So we can say, so this will be, R will be inversely proportional to the density, and the density here is represented by P. So here we can say that R will be equals, when you put the constant, so R will be equals to K over the density. So here, after getting the rate of the diffusion, which is inversely proportional to the rate of diffusion is inversely proportional to the densities of the gases, so we shall have this as the formula. In this case, we consider K as the constant. So we shall compare the rate of diffusion of two gases. In this case, we have to compare the rate of diffusion of two gases. Of course, to see the rate, it means we need to see the rates of two different gaseous molecules. So when we compare the two, their rates are inversely proportional to the square root of their density. So rate of diffusion of a gas A will be equals to the constant, which is K, then divide by the density of A. So here we can have also that here we can represent it by rate of gas A is equals to the density of gas A and the constant. So when we multiply this together, we shall have R A and then the square root of P. So this will be equals to K. So with this, we can also calculate the rate of diffusion of the gas B. So the rate of diffusion of a gas B. So this will be equals to K over the density of B. So at all we shall have R, which is representing the rate, and we can have the density of B. So this at end we can have the same formula there for the rate of diffusion of gas A. So we shall have RB, then the square root of its density will be equals to K. So when we combine these two gases together, we shall have, combining the two gases, we can have R A, which is the rate of diffusion of A, and then the density of A will be equals to K, and the rate of a gas B and its density will be equals to also K. So when we combine these, we shall have RA. For the two gases, the equation will be RA over the rate of diffusion of B, which is represented by R. The rate of diffusion of B, which is represented by R, will be equals to the density of B over the density of A, and then we get its square root. So here we know that RA is representing the rate of diffusion of gas A. RB is representing the rate of diffusion of gas B. Also the same here, we can have P here is representing the density of gas B, and over the density of gas A, then we get its square root. So since the density is directly proportional, so the density is directly proportional to the molecular mass. Density is directly proportional to molecular mass. So here this is represented by M, and the equation becomes RA over RB will be equals to the molecular formula of B over the molecular formula of A. So this, we have seen that the density is directly proportional to the molecular mass, and the equation becomes the rate of diffusion of A is equals to the molecular mass of B over the molecular mass of A. So we continue from there, and we get that considering the time, when we include time, as we know that whenever the gas travels through the air, it covers sometimes and a distance. So we shall have this comparing to the time it covers. So we shall say that here, considering the time diffused, the rate of diffusion is inversely proportional to the time. So we shall have this as, we shall have the rate of diffusion of the gases, which is represented by R, is inversely proportional to the time. So time here is represented by T. Either can be capital T or it can be a small t. So here when we put the constant, we shall have K over T. So we cross multiply, we shall have RT is equals to K. So comparing the two gases with the equal volumes, we shall have RA, and here at the end we shall have that this formula will be RA over, combining the two gases together, we shall have the time over the time for A, and this will be equals to the square root of the molecular mass of B over the molecular mass of A. So we shall have T, which is time over this, will be equals to the molecular mass of B over the molecular mass of A. So this at the end we shall have it as the formula for getting the rate of diffusion of any two gases. So with these learners we have derived the formula for getting the diffusion of gases, and here we shall have example when we come for the next lesson. So thank you very much for listening.